Right, we're going to have a look at the three-phase modules or three-phase motors and starter module, and focusing on objective 2. So this is part winding start motors and reduced voltage starters. Part of the two reduced voltage starters are going to be the auto transformer starters and the Y delta. So those are the true reduced voltage starters. There's also some code rules that you could reference for this module as well. Please have a look at those. So when we're talking about starters, there's two types of across the line or full voltage starters that you're probably familiar with. One of them is our manual motor starter, which is on your left hand side of the screen, and the other one is your magnetic motor starter. So one of the things that these will have is they'll have overload devices in them, and these are across the line or full voltage starters. That means when we energize the coil, or if I flip that switch, the motors are going to see full voltage to the motor terminals at that moment. So for the most part, that's fine. But when we get into really large horsepower motors and hard to start motors, these motors can have a huge inrush current. So if I had say a 500 horsepower motor, 600 volt, and it's roughly 500 amps while it's running, I mean, we could see anywhere from 5 to 6 times the inrush current on that. So that can cause a lot of problems. We can have all the lights go dim, brownout situations, extremely hard on the utility. So often we're going to be required to put in some sort of reduced voltage starting. And that's what this module is about. How are we going to get these motors starting and limit the inrush current to get them going? So here's a little diagram with the two types of starters here. On the left hand side, you'll see we've got a manual magnetic or a manual starter, and so they'll have, it's just going to be a manual switch. They're going to have overload heaters inside of them, so that if the motor goes overload for too long of a period of time, that will trip it open. And on the right hand side here, you see it drawn with a little bit of a control circuit. So you have your power contacts, M1 power contacts here. When I energize the coil to the starter, these contacts will close, current will flow through, go through the heater, and then to the motor. Now on this one, we also require a control circuit of some kind. So on this one, we go through our stop-start station, and so when M1 is energized, holding contact 2 and 3 close, and it will seal that holding in. So it'll keep going until we press the stop button. In the event of an overload, this here contact, the overload contact, would open and it would de-energize the coil, and our power contacts would open back up. So when we talk about these two types of starting mechanisms, this one here doesn't have a control circuit. We could have the magnetic motor starter with a as wired up as low voltage release too, as long as I used a maintain contact. But it's got low voltage release. So what's low voltage release? Well, that is if the power goes out to this circuit, and the motor will stop running. Okay, and when power comes back on, it's going to automatically restore, and the motor will keep going. So sometimes we need that type of circuit, such as a refrigerator or stuff like that, or maybe a furnace or freezer. If the power goes out, we want everything to start back up as soon as it comes back on. Whereas in other conditions, we don't want that, and so this one has something called low voltage protection. All right, and so what that means, if power were to go out and then the power comes back on, the motor will not automatically restart unless somebody presses the start button. That's the only way we can get it to restart. So in certain situations, we want low voltage protection, like perhaps a table saw or maybe a conveyor, that you just don't want that coming back on all by itself. You're going to want somebody to go and start it. So as we go into these reduced voltage starters, we're going to just do a quick little review of timing relays. So some symbols and stuff. So the coil, obviously the symbol for a coil is right there. And what we're going to look at first here is on delay timers, or time delay on energization. So when we say that, we have a set of contacts that after I energize the coil, they're not going to change state immediately until after the given time is elapsed. So if I follow this little picture here, so at this point in time, the coil gets energized, and then for whatever means it gets de-energized right here. So this little part right here is where the contacts, after this time has elapsed, is where the contacts will change state. As soon as coil power is removed, the contacts will go back to their normal position. So here we're going to look at some symbols for a normally open TDOE contact. So when I see the this symbol A here, so if I see the up arrow, that means on delay. All right, so it's an on delay timer, or time delay on energization. The fact that the contact is open means it's a normally open. So it's a time delay, normally open, time delay on energization. Other ways to write that is, you can see in the right here, we've got normally open contact drawn, and it says time to close. So that would be another way to write it, or just a normally open contact with TDOE written beside it. If it's a normally closed contact and it's time delay on energization, you'll see that we draw the contact in the closed position, and because it's a time delay on energization, it's a up arrow. And so normally closed, this says time to open, or TDOE with a normally closed contact. Very other ways to write it. Now we also have time delay on de-energization contacts. And so in that case, if it's on de-energization, here's the little graph right here of when we energize the coil. So it gets energized, and what happens here is that when it's energized, immediately the contacts will change state with it. When I de-energize the coil right here, well, the contacts don't go back to their normal state until after the given time has elapsed that we set into the timer. So that's what we call a time delay on de-energization. So the contacts would keep their energized state until the time has elapsed after the coil's been de-energized. So the symbol for, if we draw it like this, you notice that when it's on de-energization, the arrow points down. Okay, and once again, we can have open or closed. Other ways to write that is a normally open contact, and it says time to open. So if this was a time contact, when I energize the coil, it would close. When the coil gets de-energized, it would stay closed for the elapsed time and then open back up. All right, and another way to write that is TDOD. And of course, you have also normally closed contacts that operate the same way. And this one says time to close. So what would happen here is when the coil gets energized, immediately this would open up. When the coil gets de-energized, it's going to stay open until the time elapses, and then it will go back to the closed position. So that's why it's time to close. And a lot of times we'll just write it as TDOD. Right, so normally closed TDOD is how we'd say it. So there's one other type of contact that's not mentioned on here. A lot of time timing relays have IC contacts. So that's an instantaneous contact. So they'll just respond just like a normal relay contact would, where when the coil's energized, they'll change state. When the coil's de-energized, they'll immediately change state. So instantaneous contact. So you might see time contact that says IC. That means instantaneous contact. Okay, we're getting into some of our different starters. Now the first one we're going to look at is called a part winding starter. All right, so this isn't a true reduced voltage starter, but what it does is that the motor has two sets of windings, so they're parallel with each other, and they're parallel Y. And what would happen is that we would energize the first set of windings, and then within 2 seconds we'll energize the second set of windings to get it going. All right, so this is the start only winding, and then they'll both be energized for a run. Let's follow our little diagram here. What would happen? I press the start button down. What happens? S relay or coil S energizes. Okay, so that would close all these contacts right here. What else gets energized? The TR relay, so the timing relay. And you see that we've got instantaneous contacts here. They would close. So that forms the holding circuit. Okay, so right now the motor has these windings energized, but not the second pair of windings. So after the time has elapsed on this, this is a TR, timed relay, TDOE, and it's normally open, this will close. And so our coil will energize. So here's your our contacts, they close, and now we're running. Okay, so that's what a part winding starter does. So imagine, well, how does this reduce current? Well, think of these two. If there are 10 ohms of current of opposition in each one, and then I put another 10 ohms in direct parallel with them, now the overall opposition in the circuit is down to 5 ohms. So the current is much less with just one. Now we do have a risk of trying to start this motor on just one winding, depending on how heavy the load is. So there's some rules with this that we want to follow. So note the numbering. We'll come back to that. So it's 1, 2, 3, 7, 8, and 9. So going through how it starts and runs. So notice that we've got several overloads drawn here. So there's a code rule regarding that. It states that 2 sets of overloads are not required for part winding start motors, PWS, but often you will see 2 sets of overloads. So you basically are going to divide that current up in 2 and whatever the FLA is, and then you're going to size your overloads according to that and your service factor. Okay, so must be in the, so A, here are the rules, must be in the start winding. Both windings are de-energized under overload conditions and selected in accordance with the manufacturer's specs. So the 3 things that 2808 will talk about. So we also call this a closed transition starter. What's a closed transition starter? So when we're transitioning from start to run, some of the starters that we're going to look at remove the voltage completely from the motor before they reapply the voltage at full voltage. So they take away the reduced voltage for a moment in time, then the motor has no voltage across it. So that creates something called a torque pump and a little bit of a spike in current at that point when we're transitioning from start to run. So this one is a closed transition, meaning that the motor never goes without a source of energy or supply voltage while we're transitioning from start to run. All right. So there's a little graph what I was talking about there. We're going to come back and look at this again. So during a full voltage start is this one right here. Current would go, so it would rise up, the torque, and then come back down. We'd operate it down here somewhere at its full load speed and full load torque. With a closed transition starter, like we saw with this part winding, so we're going to start it out basically with one winding. The torque will start to build up, and then when we close the second one, so the speed's picking up, it's going to just immediately jump up to match about right here where it would be with a full voltage start. And so we basically going to reduce the current on the stator winding by doing this. If this was an open transition and we reduce the voltage for a second before we switch to full voltage, well, we'd see that torque really quickly go down, really quick, decelerate this motor, and then all of a sudden, boom, it spike right back up. So we get what's called a torque bump there. So a little bit about this. It's a lot smoother transition if we have a closed transition starter. So back to our part winding starter here, a little more about this. Some of the advantages of it. So they reduce the starting current to that motor anywhere from 60 to 65%. So that's what we're trying to achieve. No real change in terminal voltage from start to run. The disadvantages, they're a special order motor, perhaps, and 6 leads are required to run to the motor. So we have to run 6 wires instead of 3. And they have a really low starting torque. So they probably would not be suitable for any constant torque loads, more for just variable torque loads. So on that note, what other motor could we use in place of a part winding starter if need be? Well, in the first objective here, you read about your 9-lead motors. And if we use the low voltage setting, on a dual voltage Y motor, we could do that, because basically what are we doing with it? Well, we're doing parallel Y, right? In the low voltage setting on a dual voltage motor for Y. So if you cross-reference this back to objective 1, you're going to see 1, 2, and 3, and then you'd have to make the star, and then 7, 8, and 9 on the run winding, and that star will already be made for you right there. Okay. So a 9-lead Y motor would work for this condition here, right? So, okay. Something else, because of just using one winding to get this going, it's recommended that you energize the second winding fairly soon after, like 2 seconds. All right, and that's to avoid any complications with overheating the start winding, trying to get that motor going. So, yeah, within 2 seconds, you want to energize the run circuit as well. Okay, the next one we're going to look at here is auto transformer starters. Okay, and for this one, we're just going to look at a single phase motor here, and here's what it would look like. You recall auto transformer back when we studied auto transformer. So we have basically a tap coming off at different points, and that will give us a different voltage. So these are step down, using as a step. Sorry about that. So we're going to use these as step down auto transformers. So we're going to, in this case, we got 480 volts coming in, and we're going to drop the voltage down to 80%. So down to 384 volts going to the motor. So this motor itself, it is a 480 volt motor, but we're not going to give it the full 384 volts at the original startup. And the reason being is if I reduce the voltage to the motor, I'm going to reduce the current to the motor. So here's our parameters on this. We've got a 480 volt motor, 100 horsepower. Its full load RPM is 1,760 RPM. It's 125 amp full load amps, and it's a design B rotor. Okay, so if I wanted to look at the what would be the starting current to this, I know that a design B rotor is about 500% inrush. The FLA of this motor is normally around 125 amps. So 500% times 125 amps is 625 amps. So that's quite a significant amount of current. So 625 amps for most electrical services definitely going to dim the lights and going to wreak havoc on trying to start it up. It may cause other things to drop out within that building. So other machines to drop out because the voltage will be so reduced. Huge volt drop on your transformers and all your lines. So full voltage starting VA is going to be 480 volts times my 625 amp inrush. So as much as 300 kVA to get this thing going. So that's quite a bit. So this is where the reduced voltage starters are going to come in. We're going to try to drop that kVA down using an auto transformer. So if we reduce the voltage to the motor, we reduce the current, and we can get the VA mode of the motor down during startup. So at a reduced voltage, if I only supply this motor with 80% of its 480 volts or line voltage, we're going to reduce the current down to the motor to 500 amps. So 80% of our inrush of 625, we're going to get the motor current down to 500 amps. All right. So the VA being used by the motor, if we take our voltage of 384 volts and times it by 500 amps, now we're only using 192 kVA at the motor. So now we're only using 192 kVA at the motor. And what was that first rule that you learned about transformers? And it applies to any transformer. The volt amp input is equal to the volt amp output. So if it's 192 kVA output, we know we got 192 kVA input. What would be our line current? Well, 192 kVA, so the line current on the primary of the transformer, divided by the primary voltage of 480, knocks us down to 400 amps. All right. So we went from what would normally take 625 amps down to 400 amps. So we call this a double reduction because we have a high voltage on our auto transformer primary. That means we're going to have a low voltage or low current on the primary of the transformer. Whereas on the secondary, we get our first reduction because we only applied 80% of the voltage. We only have 80% of the inrush current going to the motor. And VA equals VA out. So what we could do with this is, if you want to know the current at the motor, the I of the motor, during reduced voltage starting, you take your I full voltage starting calculation, FVS, and times it by your percent tap. In your ILM, it refers to this as your reduced voltage over your full voltage. It's really just your percentage. So that'd be the I of the motor during reduced voltage is I full voltage start times your percent tap. If I want to know what my I going to my line side of my auto transformer is, so I reduce voltage start, we could take our I full voltage start and times it by our percent tap squared. So if I took 625 amp and I multiplied it by 0.8 squared, I would get 400 amps. Once again, this is referred to as a double reduction. So the auto transformer tapped used for starting was 80%. So the reduction to the utility is 80% squared, or the line side of the auto transformer. So essentially 0.8 squared means 64%. So 64% of 625 is 400 amp. The auto transformer, so we can use this for quick calculations. If we set this auto transformer down to the 60% tap on it, we could just go 60% squared times our I full voltage start. We could get our starting current down to 225 amps. Huge reduction from the normal cross the line inrush of 625 amps. Now we have to keep in mind the type of load we're starting. Once again, whether it's a variable torque load or a constant torque load, and how the motor is sized. So we have to be cautious when doing this, that we are actually able to still start the load. Because when we look at it, our torque that this motor produces during startup, so its full voltage starting torque, is also reduced in proportion to the square of our voltage reduction. So for example here, on our motor here, we've got a 100 horsepower motor and its full load RPM is 1,760. Well, we can calculate its normal running torque, so it's full load torque. Take our horsepower, times it by 7121, divided by 1,760. So this at full load produces 404.6. So torque full load equals 404.6 Newton meters. Well, because it's a design B rotor, we're going to see about 150% of that during startup. It's going to produce 150% of its running torque during startup. So full voltage starting torque for this motor, 404.6 times 150. So I could say torque full voltage start is equal to torque full load times 150%, if you want to write it out like a formula. Okay. Now that we've used this auto transformer, we got to think we've reduced the voltage to it by 80%. The motor's only seen 80% of the voltage, and it's only seen 80% of the current. So that means that our kVA, or our true power going to that motor, is going to be reduced by also 80% squared. Okay, because both voltage and current are down 80%. So the horsepower output has to be reduced basically down to 80%. And torque is directly proportional to that horsepower. So if I start on the 80% tap, this auto transformer, I'd take my torque, full voltage starting torque here, and I'd have to multiply it by 80% squared, or 0.64, in order to figure out its new maximum torque it'll produce on startup. And in this case, that drops it down to 388.4 Newton meters. Here's what an auto transformer would look like, and this one we are looking at an open transition auto transformer. You see that there is 2 auto transformers in there, so it's basically open delta made with 2 auto transformers. And so how does this work? Well, during the start period, the S contacts would close, energizing the auto transformer and allowing us to take the taps off, and we'd see 65% of the voltage. So this is a 3-phase auto transformer. And then we'd transition it to run, so that means that the start contacts would open up and the run contacts would close. Now it's got full voltage, the motor, and yeah, so that would be, we have one of these in the lab and you're going to see it. It's a manual handle with the door interlock and the stop. So this is the exact diagram of the one in our lab that you guys are going to get to see and try. Here's a closed transition auto transformer. So what this does, once again, the motor will always have some sort of supply voltage on it as we go from start to run. Let's go ahead and follow this through. So starting on rung 1 here, we press the start button. So the start button goes through this normally closed contact of the timing relay, energizes coil 1S. All right. What else does it energize is the timing relay. We've got a set of instantaneous contacts then, acting as a holding contact from our timing relay. And so let's go ahead and draw 1S closed. So as you see here, it hooks up the 3 auto transformers basically in Y. So what else would happen here is current would also flow down. And we see we have a normally closed contact, R contact, so 2S would also energize at the same time. So here's our 3 auto transformers connected up in Y, and there's the tap off the middle of them to go to the motor on each one right there. All right. So right now the motor is started and it's operating at a reduced voltage when 1S and 2S are closed. It's just like that. Okay. So this contact is open, and this 1S contact is also open here because 1S is energized. That's a normally closed, so we call that an interlock. So 2 of them open in series then. So what happens when the timer times out? Okay, so the timer times out, so that means its contacts are going to change state. So starting at the top, TR, this first one, will open. All right, so that controls contact 1S. So 1S opens. So for this brief period in time, during this transition, we still have a path through the auto transformer, half of the auto transformer winding, to get to the motor. All right, what's the next thing that happen after that? If 1S de-energizes, all right, so that's the end of that. The other time contact then is going to close right here, and this contact goes back to being closed because 1S de-energized. So then our contact will energize. So our contact energizes. That would close, okay, and this would open. So due to the order in which it goes through the rungs, is going to leave full voltage or leave a voltage on that motor winding while it transitions. So this goes to open, 2S that would then de-energize. So no path there anymore. Oops. And we're back to, or we're at full voltage now going to the motor. The auto transformer windings aren't being used. So that's a closed transition auto transformer. We got one of these in the lab that we're going to show you as well. So our last type of reduced voltage starter is called, well, second last I guess, is called the Y delta stator or starting. And you might be, if you've already completed your code work, you've probably seen Y delta mentioned in the code book for when you're on table 29, as possibly with overloads as well when you're sizing overloads. So we're going to have a look at the theory behind that. So if we look at a six lead motor, and so we see that there's coil 1, 4, 2, 5, and 3, 6. And if we make the star with 4, 5, and 6, we now have those motor windings connected up in Y. Versus the diagram over here, we can go 4 goes to 2, 5 goes to 3, and 6 goes to 1, and then we supply 3-phase power. So we can also connect them up in delta. All right. Well, what's the difference here? If you recall back in theory, when I go from Y, connect the load up in Y, and I take to the same supply and I reconnect it into delta, we're going to see 3 times more current. So it's advantageous that if I started at Y, I'm going to get 1/3 of the current on startup as I would if I were to start it in delta. So we can use this to our advantage. So here's a little example here. If this is out of each one of these coils is 1.2 ohms. First, if we look at it in Y, well, the phase voltage is going to be 120. So we could calculate the phase current. 120 divided by 1.2 would be 100 amps. And we know that line current is the same as phase current. Over in delta, each phase is going to see 208 volts. So our phase current will be 208 divided by 1.2. All right. So now our phase current is at 173.33. Line current is going to be my phase current times √3, so 300 amps. So we see that the current is 3 times greater in Y than it is in delta. So we're going to take advantage of this. So I line and delta, yes. The VA is produced, if we were to run this through the 3-phase formula, V line times I line times √3 is 36,026.6 VA. In delta, with line current being 3 times greater, we're going to get 108,080 VA. So 3 times the VA, right? And therefore, it'll be 3 times the power, true power, because it's the same power factor. These are the same coils, and 3 times the horsepower. So windings connected in delta compared to the same connected in Y to the same supply voltage will produce 3 times the horsepower and 3 times the torque. So another quick look at that. All right. So here we've got a 6-lead design B motor that will have a starting and rush current about 500%. So if we were to go through this and figure this one out the same way, our phase current here, so 480 divided by √3 is 277. Phase current is about 35.89. The phase voltage here is 480 divided by my 7.718 ohms, 62.19 amps. Line current the same as phase current. Line current is √3 higher in delta, 107.7 amps. Running it through our power formula, V line times I line times √3 times power factor, we're going to produce about 14,920 watts. The true power when we connect it in delta, 480 times 107.72 times √3 times 0.5 is going to be 44,778 watts. So we see 3 times more power. Now if I convert that to horsepower, so I take 14,920 divided by 746, we're about a 20 horsepower motor in Y. And do the same thing for delta, we're looking roughly a 60 horsepower motor when it's connected to delta. So same motor, reconnected from Y to delta. So here's a Y delta open transition starter. Let's go ahead and follow this through. So if you notice that we've got 3 sets of power contacts. These are our start right there, or star I should say. They make the star when I energize the 1Ms. They'll make the star. I better wire this up. So there we go. So T1 goes to 1, T2 goes to 2, 3 to 3, and then 4, 5, and 6 come back. And yeah, so that's how we'd have 6 leads going out to the motor when we have this motor from our starter. Okay, so our Y delta control circuit. Let's have a look how this is going to operate. All right, so we start in the Y connection. All right, so I'm going to press the start button right here. What happens? Control relay CR energizes and our timed relay energizes. Control relay CR creates a holding circuit. So it stays energized, CR stays energized, and so does the timing relay. Well, what else does CR do? This normally open contact here closes. It allows current to go through our timed contact, which is a time delay on energization, and normally closed. So current would flow through. 2M is normally closed. So the S coil would go ahead and energize. So now all S contacts close. So we see S contacts closed. Okay. S contact closes. All right, well, when this S contact closes, it energizes 1M. So 1M contacts close. What else energizes 1M? Well, this one right here. That acts as a holding contact. Okay. And this one would, right here, would go to an open. So that would open. Whenever S is energized, that normally closed will open. So 2M is not energized right now. So if we follow our diagram here, line 1 goes through 1M, goes to T1, and through T1 to T4 coil. It comes in, and the motor right now, it's the same on each one of them. It is connected in star or Y. So what happens when the timer de-energizes? Well, in run, we're going to go to delta. So the timer opens up right there. So current would, so that would open up. That means S coil would de-energize. When S coil de-energizes, this would go back to open, but we still have a holding circuit here. All right, so 1M stays energized, and the S contact here that was open for us now goes to the closed position. So 2M will energize. Now what do we have? Well, we have the windings connected up in delta. Let's just give you an example here. So if this is big A, this side is little a. So big A, little a, big B, little b, big C, little c. We could follow it through. Little a goes to big B. Little b goes to big C. And little c here goes back to big A. So we're in delta. All right. And that's the run. So we're going to run in delta. Press the stop button. Everything will de-energize. So that's our Y delta starter. Note where the overloads are. They are in the phase. They're not in the line. All right. So when the overloads are in the phase, that means I have to take the FLA of the motor on the motor nameplate, and I'm going to have to divide that by √3 or times it by 57.7%, and I will get the phase current. Then I can apply my service factor to that, whatever it is in the code book, 1.15 or 1.25, based off the nameplate service factor. So just keep that in mind, that those overloads there's only one set of overloads, and they're going to have to be reduced to the phase current before we apply the service factor. Having a better look what it looks like in delta here, and we can recall the sequence of events. When we first pressed that start button, we saw that 1M contacts closed and the star contacts closed. So right now, these windings are connected in Y. when the timer timed out, the S contacts opened and the 2M contacts closed. Now it's connected in delta, at the overloads being in the phase. The overloads are in the phase. So Rule 28-306, sub Rule 2 applies to these overloads. We also have a closed transition starter when we're talking about Y delta. So what they make use of here is something called transition resistors. So we could go ahead and it's kind of the same sequence, all right? So what we're going to do here is kind of run through this sequence. So at the beginning, when I pressed the start button, same thing happens. 1M closes and the star contacts it, or start contacts, start. So right now if we follow it, they are connected up in Y. All right. So the next thing to happen is when the timer times out. So what would happen? The transition resistors, T for transition, would close. So we have a parallel path there. Then our star contacts would open. Now this happens very quickly. All right. So these motor windings are always going to have some voltage, some sort of current going through them, or a supply on them during this period. Next thing to happen is that 2M contacts will close. And the last sequence is the transition resistors will open up. So I'm not sure if this closed transition diagram is in your ILM, but we have closed transition starters for Y delta as well. And for those you would need transition resistors and a fourth contactor. So once again, the torque bump is reduced because we have a closed transition. We would just be trucking along, and instead of it dropping down like it would in an open and then shooting all the way back up, it's just going to do the one bump up to when full voltage is applied to it, and the motor will keep accelerating, and then we will operate it at full load somewhere in that area right there. Oh, there's full load speed right here, that line. So open transition, once again, reduce voltage charges, remove motor from winding from power to source when transitioning from start to run, causes a considerable torque bump, whereas a closed transition, reduced voltage starters do not remove the motor winding from the power source when transitioning from start to run, and this causes a smoother transition with minimal torque bump on the motor and the load. All right. So there's the one other method that would be more common nowadays, was if we were to use an electronic soft start, or we could use a VFD. They are doing two different things. So a soft start is just cutting off part of the sine wave, making the voltage be reduced. There's a couple of different, so through electronics, there's a couple different modes in which you can accelerate that motor, ramp starting and current limit starting, or they may have a kick start, and that's just to give it a surge to get the load going. So you guys can read up on this. There, a lot of times if you have to go in, you may have to troubleshoot some of these old reduced voltage starters, and sometimes you're just going to go in and have to replace them, and you'll probably end up putting in a soft start or a VFD or something similar. This chart is in your book, and it's a good little chart just for as you go through your examples here, and it's a little summary. One of the things that, so part winding, you're looking at roughly about 65% of the current of a normal inrush. Torque is pretty low, it's about 48% of the normal full voltage starting torque. When using an auto transformer, we reduce the voltage to the motor by 80%, for an 80% tap, 65, 50, depending on what tap you're on. Now the current is also reduced at the motor by those same percentages. The line side of the auto transformer, or the utility side of it, well, that's where we experience a double reduction. So if I knew the normal inrush current of that motor, and I wanted to know how much current is going to be on the supply of the auto transformer, I could take my 80% squared, which is 64%. All right, so we could have down to 64% on 65%, roughly 42, 50% is 25%. Torque, also, the produced torque is also proportional to the square of the percent voltage reduction. All right, so if I reduce the voltage to the motor by 80%, 0.8 squared means that I'm only going to have 64% of the normal starting torque, okay, during reduced voltage starting. And same thing, 42 for 65 tap and a 25% of the normal starting torque using a 50% tap. Why delta? Well, we reduce the voltage because we're only going to be down to 120 divided by 208, right? So that's 57.7%, or 1 divided by root 3. So voltage is down to 57.7%. We know that the current's going to be a third, or 33%. Okay, and because the current, so basically if we take 0.577, 57.7, and square it, that is also 33.3%. So it too is proportional to the square of the voltage reduction. So 57.7 squared is 33. And because our voltage is down and our current is down, our torque produced is still proportional to the percent voltage reduction. So in Y delta, it's a little bit easier. It always works out to 1/3 of the normal full voltage starting torque, or 1/3 of the normal full voltage starting current. So stop starts adjustable and wound rotors, very good. High torque, we got some speed adjustment width to them. Current is good, so just that they're big, bulky, and they require a lot of maintenance. So that's about all I'm going to have to say about reduced voltage starters for now. I'm going to try to do some examples up for you guys next week, and look forward to seeing you then. Talk to you soon.